Dr. Paris Arvon Lockett, and today we'll be talking about a review of beam theory. A little bit ahead of having to analyze these beams in SolidWorks to give you some background on where beam theory comes from, refresh your memory, and then in the following video we'll actually do some hand calculations. You always want to try and, if you can, validate your, or really they call it verifying your simulations against some analytical theory just to make sure your simulations are in the ballpark. And then you can start doing some more complex stuff, doing some parametric studies, changing around some dimensions or variables or material types or geometries, but you always want to have some baseline that you know is right if you can. In engineering, a beam refers to a slender bar that carries transverse loading. That is, the applied forces are perpendicular to the bar. What does that mean? Well, here we're showing a beam that's running the length of the ceiling above. It's supported on these columns, and it carries the weight of that ceiling, and we call this, if you recall, a distributed load across the top of that thing. You notice that that load is perpendicular to the axis of the beam itself. The basic analysis breaks the problem into the beam, its loading, and its constraints. Here we show the beam. Here we show an external load, W, a distributed load per unit length, and then the constraints. On one end, we have that the beam is built in, which adds its own reactions, and on the other, we have that the beam is free, which you might guess means there's no reactions at all. And we use this in an equilibrium sense, summation of forces, summation of moments, to actually analyze the beam to find the internal forces and moments acting on it. Analysis further looks at the whole beam and looks at the beam in sections. So in the top, what we say is that, yes, let's analyze the full beam. And this full beam, we can draw a free body diagram. We would necessarily apply then reaction forces, reaction moments to the beam. And those reaction forces and reaction moments are then equilibrated by our distributed load W here or any other external load. In addition, we can make a cut, and that cut then exposes an internal shear force V and an internal moment M. Both of these vary with position X, shown here along the length, and still have to be equilibrated with our reactions, here R in the Y direction, and our moment reaction, MR. Notice the convention here is that MR and MR make a nice smiley face, which is our positive convention for moments. One solution procedure begins by finding the external reactions, and then it finds the internal forces and moments once those external reactions are known. So consider the beam on the left, where we've used summation of forces and moments on the whole body. Doing this, we can set up a system of equations that will tell us our reactions with respect to the location and the magnitude of our distributed load W or any other load. And then, once we make a cut to expose the internal forces V and M, our shear and moment, we can again do summation of forces and moments with respect to whatever external loads are present on our cut face and our reactions, which we should now know. This will yield our shear and our moment. So we can use that to actually solve the problem. Why do we go about solving for these moments and these shear forces? Well, the stresses in the beam are dependent on these internal forces and moments. These internal forces and moments give rise to two types of stresses on a transverse section. First is the normal stress sigma, shown here. The second is the shear stress tau, shown here. Now, the normal stress depends on the moment M, y, which is the distance from the neutral axis, and I, which is the central moment of inertia. And our shear stress tau depends on VQ over IB. You may have forgotten that one, but V is the shear force. Q is that first moment of area about some location Y on our transverse section. I is again that centroidal moment of inertia, and B is the thickness or width of the beam at the section we're dealing with. Generally, we don't apply tau, we don't solve for it because the stresses due to tau and the stresses due to sigma are much more driven by that moment than they are by the shear force. So when you're looking at beam failure and analyzing beams, generally all of your focus is on sigma, especially if the beam is long and slender. And so you don't have to go looking for them all. Here are some useful relationships. Maybe these will spark something in your memory. The maximum normal stress, what we're going to be dealing with here, sigma max equals m times c over I, or m and I we defined already, and c is the farthest distance from the neutral axis, either top or bottom. So c is going to tell us how much that linearly varying stress, if you remember that, increases the farther we move away from our neutral axis. So the taller the beam, the higher that sigma max. Our max tau is VQ over IB, where Q is that first moment, but here about the neutral axis, the first moment of area. If you are interested in calculating it, it's the integral from some position above the neutral axis y1 to the maximum C, and then integrated over the area dA. And then if you recall the centroidal moment of inertia, it's just the integral over the whole height of the beam of y squared dA. Alrighty, so the basics we have for analyzing it are, we have to look at the beam itself, the forces, and the constraints. Those forces, external, lead to some forces internal, which are the shear of the moment, and then we can actually begin to solve for the internal stresses. But, as I said, we need to know what's happening at the supports, because that's where our reactions are generated. Two straightforward types of reactions here we'll go over. The first is simply supported. Simply supported means that we have a pin connection on one side, a roller connection on the other. This type of support only suppresses the transverse displacement. What does that mean? That means that the beam cannot move up, can't move down. Yeah? And it also can't move left and right, but in this type of analysis, we don't actually deal with motion along the length of the beam. So at R1 and R2, the beam just can't move up or down. Because it can't move up or down, typically because the load here, P, is going down on it, then we can actually write an equation for summation of forces, and we can also write an equation for summation of moments. Note that we have two equations, and we have two unknowns, R1 and R2, which we need to actually solve the problem. They have to balance. Our second classification that you see often is a cantilever beam. Here on the right side, it's built in, which generates some sort of reaction moment, generates some type of reaction force, and here we're just showing a distributed load W all the way across the top. So at one end, it's built in. The other end, it's free. So at the free end, we have no reaction, and we have no external load acting there as well. So no forces and moments at the free end. The built-in support also prevents displacements as well as rotations of the beam. So if we were solving for them, we would actually set some boundary condition that says the displacement is 0 and also the slope is 0. Whereas in simply supported, the slopes don't have to be 0. Our final type is an overhanging beam, which consists of a pin on one end and a roller support on the other here, with both ends of the beam extending beyond the supports, which is a little different than the cantilever or the simply supported. What's interesting as well is that, as with the others, we have two unknowns. Here R1 and R2. And what this means is that if we do summation of forces in the y, and we do summation of moments, we can generate two equations, and since we only have two unknowns, we can solve this problem. That means it's statically determinate, because the support reactions can be found directly from the equilibrium equations, which is useful. Also of interest is that based on the supports, this beam is broken into several sections. We have one section to the right, one section to the middle, and one section to the left. Now, we can also divide sections based on the loading, which we'll see in our example problem later, but here, They're clearly defined based on the supports. Well, thank you for watching. Thanks for participating. Hopefully this has sparked your memory for beam theory, got those juices flowing. In the next video, we'll actually run through a demonstration problem, and that'll help you on the next homework where you're going to solve a problem by hand using beam theory, and then also try and do a simulation of a beam in SolidWorks and compare those results.